Okay. Okay. So the title of this course is Advanced Optimization Techniques. Number one. So there is number two. Okay. So for, well, it's actually covered how do we implement several techniques, several tools to solve optimization problems. And the emphasis on this course is that the optimization problem that we are going to solve is mostly basic optimization problem, which is you may already or it will be extended from the problems that you learn from operation research courses. So I guess for all undergraduate, master degree, and PhD in IE or engineering management, I think OR will be like basic courses that you may already take before this class. So, but anyway, the problems will be mostly deterministics in which several parameters, several variables is simplified so that it's assumed to be known in advance. Later, I will cover more detail about that. And originally, since we learn about the techniques and these tools is quite robust that you may apply in several fields. So it will be very interesting if we try to cover all of those application in all of those topics, and it may not be able to be compressed into one course. So that I decide to just borrow several problems from logistics, operation management, and supply chain management area to be applied or to be solved using the techniques that we are going to learn in these courses. So, but anyway, if you have other topics that is not covered here, especially for PhD student, you may explore several topics that may interest for your research topics, but somehow you see the possibility of utilize the tools that we learn here. I think I am also open for discussions if you need to, how to say, mix and match how to use the tools for your particular problems. But still, I will still continue with in the class. We will stick to the plan that we make in the syllabus. Okay. Okay. Uh, there's not much change I did in the course outcomes because I think this will be uh, need some administration things to do if we need to change the course outcomes, so that I keep it that way, so that the level of or the goals of the materials that I prepare for this class would not be at least would not be less than what are the school plan for outcome of this course. So we are hoping that after this class, after taking this class, you will able to at least formulate mathematical models and then solve problems using tools in like computer software or that applied those techniques that we learned, mostly related to operation research, and also applied tools that we hope, especially I designed it for the projects that we can solve some real industrial case problems that you may select by yourself as the participant of this course. Okay, and the course is designed for 11 week, in which it consists of one midterm exam week and one presentations or project presentation weeks. So basically it will be the learning, teaching and learning activities will be conducted only in 9 weeks. And at the earlier stage, in the first until 4th weeks, we will cover some, sorry, until the 5th week, we will cover some review, a little bit of review about the problems, and also we will take a little bit look back on what we did. We learned the several basic things about OR, integer linear programmings, and then we move on to how to use tools such as Excel Solver or some more advanced mathematical programming tools like AMPL, Gurobi Solver, and Cplex Solver. And I also embed the utilization of analytical hierarchical process tools, AHP, which is very common actually for the decision that may try to absorb several experts' opinion on the decision making process. And I think some research also combine these tools with optimization tools. So I think it's also good to put it in the beginning of the semester. So I think for this tools, I consider it's basic foundation if you want to do research related to optimizations. Okay, so I put all those basic and foundation things up front before the midterm. Why? Because I'm hoping that those basic foundation can help you to decide and perhaps start early working on your projects. So I'm hoping that for the optimization projects, I will announce it today so that you will have about 10 weeks to work on those projects. Okay. And for PhD student or for any sit-ins participants that also want to like elaborate on collaborate on these projects, you are all very much welcome. Okay.
Publish journal. Publish journal.
Even if you already have the topics and then you want to like combine it and collaborate it in this how to say particular courses, extended using the tools that we learn here, I also will be very much appreciate that, because that could be good example for the next or for like how to say improvement of this course in the next term. Okay, okay, I already explained until week 4 and 5. Next, after midterm, well, the midterm, I think it will be online exam. You may need to like review several exercise that we already did and assignment that we will you need to collect in the in the topic before midterms. And after that we will start about a little bit more on recent techniques that that is often used in the where, well, both in industry as well as in the research. So for PhD students, if you want to how to say uh, cover some you may also found these particular tools and techniques discussed in the paper that you perhaps may review right now. So I think I will let this part after midterm will be more about discussing the techniques that we call meta heuristic techniques. However, meta-heuristic technique also have many branches. So in order to have a nice learning curve, so I guess I will start from a very popular one. For example, here I write particle swarm optimizations techniques, since this meta-heuristics tools is very robust and popular. It can be used for, and it already reported to be successful, to be applied in so many optimization, not only optimizations problems, but also many others tools, problems outside the topics that we are discussed in this course. So I hope that at least for after the midterms, PhD student can be more active and more, how to say, I will be how to say, encourage more discussion from you, so that we can have so that I can also improve the way I deliver the materials. Okay. The reference that I use for this course actually, originally I planned to just use one books, but somehow one books doesn't cover all of this topic. I think that using one textbooks and then deliver most of the material from only one textbooks is not really suitable for this course in particulars, because we will take several topics from one books and one other several others from the other books, because as you can see that uh, if we want to make it basic optimization techniques, perhaps it can be from just, okay, just take one book, cover all the materials there. But I think that since this is a graded courses, so I think this way might give you some perspective that if you want to learn some things, you need to explore something like that. So you can't only learn, okay, it's a good foundation to get all the material covered in a one book, but I think that is more suitable for undergraduate courses. For graduate courses, I think this way will be, how to say, yeah, it's quite challenging, jump one from one topics to another, from one book to another, but I hope the way I mix and match the topic can help you to grasp the knowledge that we all want to learn here. Okay, the assessment will be comprised of um, one midterm, one assignment, 3 exercise. The exercise mostly will be conducted online during the class delivery, and one optimization project, as I mentioned earlier. And the grading will be looks like this. I think this is default from the previous um, previous templates that I've just modified a little bit by adding the optimization project instead of the final term exam. Okay, up until this point, do you have any question you would like to ask? Please.
So which journal should we submit, or which journal is the target?
Well, okay. So we should start from the project then. Okay. The journal will be related with the project, right? So, Well, actually, I'm not going to strict to which journal you need to submit, but
But you have to submit, yes.
but I'm aiming to make the journey a little bit interesting by having a goals in mind, something like that. So start from the first assignment. I will design the assignment exercise, no, perhaps not the exercise, the assignment and the monitoring of the progress to help you with the journey of completing the optimization project. Okay, first, for the assignment one, which I will release today, I may want to ask you to find a article that published in SCI or Q1 Scopus Index Journal, which cover the application of optimization techniques, in which you can see from the syllabus. But the topic will be not limited to what we are discussed in the class. For example, we discuss facility location, vehicle routing, and but you can also explore any areas that you are interested. For example, like Arvin yesterday told me he has like data mining's approach to do some classifications. Perhaps if you want to combine the to optimize the parameter or future selections in the data minings, you improve it using PSO. That's also very much welcome to be how to say, to be applied as optimization project if you want to participate. But for the master degree students, I think since you may, well, if you're taking a Dr. Yogi class, you may already experience this type of assignments. But if you may not experience that, I will also provide the opportunity for you to have those experience, but not to be too how to say, make it hard for you to accomplish that. So let's make this journey how to say, completable. Can I
Ikigai,
say that?
ikigai.
Yeah. Okay, so first, you if you want to make something good, you need to refer to something, so you need to see what let's say if you want to make a good paper, you need to read a good paper, right? So I will ask you to find one good paper which is indicated by it is published in SCI or Q1 Scopus Index Journal, and then make summary from that paper, cover the main topics or main discussion from the paper. For example, the problem descriptions, the optimization technique being used, the result, how they conduct the experiments, and the future research directions. Those points can be can also be your guidelines for completing your optimization projects. Okay. Uh, Next, from that one, you may also reflect, okay, this kind of thing I will do. So next, you will need to form a group of 2 or 3 people to implement optimization techniques in practice. So it means like doing optimization technique by benchmarking with previous literature may take longer times compared to if you already have some practical data, practical case that you already have in hand. But not many people has those advantage. For example, you may find this kind of practical application if you work in the industry, or you have the relation or connection to those needs for the application of these techniques. But since not many people may also have those kind of opportunity, so if you doesn't have, I also able to provide to you several cases that you can work on, even though the data may be strictly confidential, but we can ask them for the how to say, part of the data that already being randomized, but still mostly represent the real case that they're being studied. Okay, and then if you want to apply mathematical programming techniques, it's good. But if you don't want to apply that, that's also possible. But you may need to choose like more how to say, more, I would not say difficult, but more challenging, a little bit more challenging techniques like heuristics and meta heuristics. But of course, research, if you conduct this for your research, sometimes the more techniques you apply, the merrier. Even though like in practical point of view, it's not always like that. Okay. But since we are aiming for publish your project, so I guess you may want to use the paper that you read in the assignment one as the baseline. Okay, so if you see, okay, they do something like this, let's try to at least cover something like what they have. Okay, and then for the application project, this one I already mentioned earlier, like you I'm not strict you with the topics that covered in the class. So you do not have to wait. For example, I want to do a facility location problem, but facility location will be covered in the 4th or the 5th week of this class. So I will not suggest you to wait for the topics being discussed, but sorry, wait. Okay. Wait. Screen two. Okay. Yeah. I will not suggest you to wait, but just start as soon as possible. Okay. And we will monitor the project weekly. So after the class, I will ask you to like update the progress of your project, so that
So
I can.
this is 2 to 3 people.
Yeah, so it's only one group actually.
Okay.
Because
Artfin, are you free with me? Can you join with me, Artfin Ong?
Can
Artfin.
we do the project by August, please?
I know you're busy with your
Okay.
dissertation, but
But
it's
that's
okay, Artfin. I'm also want to join this one too. Yeah, I want to join. Although I'm
Okay,
just sitting.
maybe
Yes.
Yogi will be one group with me and
Oh yeah, I've group with you. I've group one group with you, me, you, and then Dean Young.
Din Yang. Okay.
Me, Gru, you, and Dean Young. We can. Dean,
Let's do
you
the
have so
project.
many. Dean, you have so many data,
Okay,
right,
okay.
Dean?
Okay. Yeah, we have the data.
You have the financial data, so many, you know. You have it.
Dr. Serrano gave the data.
Okay.
Okay, yeah.
Okay, great. Let's do this as well, so that we can give the example for the student as well. Okay, and the final report will consist of two part. First is the presentation file that you will present at the end of this class, and report that in the form of a journal that you will submit to the system. And since the class will be end at the I'm not really sure whether the August 9 or 1 week after this, but yeah, somehow I just put the deadline on August 9 first. Okay. And to give you a little bit of okay, this one is just a simple guidelines, so you can read it later. This basically follow the format of presentation, academic presentation, and how to report the experiment in a paper. And this is the interesting part. um, if you I would like to give you some ideas that you may, or how to say, I'm not sure if you find this interesting, but for me, I think since optimization projects that we want to apply here is the one that we want to see how it really applied in the practical point of view. So here's some project that I think it's a nice topic, since it's cover some current situation that are being hotly discussed in media, in news, something like that. And actually, this one is I take this one from I forgot the organization name, but they make a challenge in a term of competition. So if you have ideas on how to apply OR and or AI techniques to help the how to say decision making during that related to COVID problems, you may also have you can follow the competition. For example, how to optimize vaccine distribution, select the location of vaccine facility, and scheduling the crew that will be pretty much related with this course. Or this one is, I think, a spatial issue, but this is not a good journal, but they provide a nice idea. It's about how to create a more resilient and sustainable supply chain, since we all see the impact of how the pandemic that is currently faced by I think all the companies around the world, makes the decision maker, especially in the supply chains, need to think whether their current supply chain will be will need some improvement so that it can become more resilient for to face this kind of situation in the future. Okay, those are several topics that I want to deliver for the project and the assignments. Okay, any thought about that before I start the material for the first week? No? So Dr. Yogi and Din Yang, so we will make one paper. hopefully, okay.
Hopefully, yeah.
Okay, so well, I actually refurbished some slides from the class that when I invited to one of the class from Dr. Yogi last month or last 2 months. Okay.
Last month.
Last month.
Yes.
Okay. But anyway, please let me continue to. So the screen is still working, right? Share screen.
No.
No.
I cannot see anything. Yes.
Cannot see anything. Okay. Let me.
Anyway,
share.
Dr. Vira,
Yes.
Dr. Wu, you know Dr. Wu, right? He
Oh,
is the
yes,
editor.
yes.
Yeah, he is the editor of the guest editor of one SCI journal. Perhaps you can submit to
The
his
circular supply chain, the one
yeah,
that,
the circular supply chain. It's SCI. It is
yes.
SCI. Yeah, it is SCI journal. So and the chance is high since well, uh, Dr. Wu is there, so it's our friend. So he will read like, oh, this is created by Dr.
At
Wira
least,
or
at
me.
least it would not be like desk rejection from the
Yeah, it's not
editor.
dash rejections. Yeah, at least he will just accept it and so on.
Yeah.
Big chance for everyone. Yeah, Natakit,
Okay.
for example.
Yeah.
Yeah.
Yeah, Natakit, you can use those opportunity. I will
Yes.
also share the link to all of you guys later.
Okay.
Okay. For the first week, introduction to advanced optimization techniques. We will discuss about, wait, where is number one? Okay. Several things yeah, since it's introduction, so I will start from introduction about optimization, and I will review a little bit from operation research that well, it's closely related with optimizations. And one of the techniques known as linear programming and several models related to operation research, then that is formulated using linear programming and various example of optimization problems. But since I think all of you are taking the research seminar that provided in the PhD course last time, so those example of optimization problem, I think we already covered some of it in the last meeting. And optimization in logistics and supply chain, well, it's actually combined 6 and 7, those examples. Okay. Okay, first, the course outcome. This will be, from this slide, we will learn mostly about how to formulate mathematical models from definitions that given, or it's the situation perhaps like, okay, you when you discuss with someone from the industry, they may not really, they will know the problems, but they will not be able divining exactly or as beautiful as the formula that you can formulate easily in the form of mathematical model. So we will see some of the examples, and hopefully the after studying and then taking this class, you will get we will be able to do this CO1, course outcome number 1. Okay. Next, first of all, since we are doing optimization, okay, wait, I forget one thing. Before I start, actually, I want to make a rules that this is also suggestion by the general medical practitioner that just examined me since last week. I got a back pain, Dr. Yogi and Dr. Yang. Hopefully will not happen to
Because of
all
the
of you
age,
guys.
perhaps.
Too
Because of the
many
age,
sitting,
perhaps.
too many Zoom meeting. So,
Yeah.
okay, for this class, I plan to do it like this. For the materials in this course, I will split it into 15 minutes material delivery and 5-minute breaks. Okay, so all of you guys can have those 5 minutes breaks.
But during this break, they will sleep.
At least it will be beneficial for me, right? So so please understood about this condition if that's the case. Yeah, I'm not
Okay.
worried about how to say the whether it's not effective or something like that. But I think as long as this one being recorded, so we can like rerun again if you somehow miss several part of it.
I think you should ask someone to massage you when you teach, so that's another option. another option when you teach, someone massage you. I think Dean Young is actually doing that.
Yeah, that's a good idea actually. Okay.
You can ask Dean. Dean Young.
Okay, perhaps next
Okay.
time I will
Yeah.
like try Dr. Yogi's suggestion. Okay. I'll start the 15 minutes clock now. Okay. First of all, since we are talking about advanced optimization techniques, I will break down the word of it first. Sometimes we talk about optimization, but optimization is being used in many, how to say, many, many, uh, many communication, many sentences that may or may not related to what we are going to talk today. uh, but mostly, if we talk about optimizations, the word will be a rhyme or in similar or have a synonyms with optimize or improving some things or enhance something. So, borrowing the term that is given by uh, this researcher, I don't know how to read those beta, whether it's B or no, but let's if I'm not mistaken, Forbes and Woodruff 2006 in their books about computational optimization models, the word optimum means the best. So when you said I want to do optimization techniques, so you want to use a technique to find the best. Now, the best of what? Now, here, to be more precise, optimizations mean to attempt to find the best possible solutions to a particular problems. Okay, so here we have another two keywords. There is a solution, there is a problem, and you want to find the best of the solution for those particular problems. And operation research, well, actually, operation research somehow has the same perspective with doing optimizations. Instead, it is actually optimization. It's actually sometimes have a same definition with optimizations, but it's more applied for the academic use. Okay, so as the name implies, operation research, we can see that there is, or we can say, research on operations. This means that how do you apply, or how do you conduct operations which apply to many areas, for example business operations, or in a more scientific and structured way, so that it can be run more efficiently and effectively. So the beginning of the operation research, well, actually uh, attributed or originated from the application of those techniques in military services or military operations during the World War II. So, but since the applicability of these tools is can give so many benefits for the conduct of this activity itself, many areas start to apply the techniques in their respective field. For example, manufacturing, and because after the military booms of the applications, we have the industrial revolutions, most likely in the manufacturing, and then we have military manufacturing area start to apply it, followed by transportations, construction, telecommunication, financial plan, healthcare, and many various areas. Okay, and following the technological advance of computer revolutions, these techniques are gain much leverage because many of the techniques are heavily related or heavily need or rely on computational stuff and, well, basically mathematical and statistical stuff in their basic foundations. So when you have a machine that can do those calculations more efficiently, more effectively, and the study or the fields of the studies also gain advantages. Okay, so start from, we can say, the computer revolution. Well, it's actually start earlier, since when the IBM start introduced the very big size of computer, but it's actually really start taking off since the many people can have access to it. So like the start of personal computer, perhaps we can say 1990s, like all the people, every people may have one computer in their, or one machine in their home. And later on it becomes how to say, uh, uh, seamless with the application in the business. So sometimes you won't even see the terminology of operation research or optimization tools and things, but it's actually hidden under the beautiful user interface of software that actually used to help you to manage to optimize many decisions in your business area. And the fields, the terminology shifting from using operation research into business analytics. So basically, when you learn all those things from OR, optimizations, business analytics, basically they may have like intersections in the discussions. Okay, so what is analytics? For short, or but maybe it's oversimplified, we can say it's similar to operation research. Analytics is the scientific process of transforming data or how to say, fact that you understood from the situations into insight, so that you can make a decision for insight that you can use for decision making process. Okay, but what the details will be many, but those are the I think basic explanation about this. But why do we interested on this operation research, and how will it relate to the optimization techniques that we will learn today? Okay, let's say we are making decisions. You can make decision in many events. Okay, for example, if you have if you are running a business, okay, business will so if you want to serve your customer, you don't want your customer to wait for a long time. Uh, let's say it's a restaurant and you want to your customer not waiting for so long before you can be able to deliver what they order. So perhaps you may need to prepare several pre-cooked meals as an inventory, for example. Those are decisions. How many pre-cooked meals you should prepare so that it will not be being unused, something like that. Or what is the optimal number for the inventory that you need to keep to be in order to fulfill your customer demands. Too many inventory is not good. Less inventory will be not, will make you not able to respond the customer demands. Okay, those are decisions. If we have to make the best decision possible, what should we do? Okay, so one good option is to evaluate as many as possible options that can be used as the decisions. So later on, you can choose from those options by weighting the pros and the cons. Okay, and in operation research, um, this kind of things is addressed as how do you make the best decision under several constraints. Those are operation research. Okay, and it can also be written in well, this is general mathematical terms, as you can maximize or minimize the effect that being raised by the decision that you make. Okay, and those decisions will need to consider or meet several constraints that is need to be faced in the problems that you are being considered. And those OR techniques, or the things that you learn in OR, we can classify the problems or classes that being solved in OR into uh, three big category. Well, even though this is not really precise, but somehow, yeah, these three category quite represents what you learn in what kind of problems you learn in OR. First, there is optimizations class of problems, in which we will much cover in this course. The advanced optimization technique one. So, and then in which it's normally emphasized on how do you how would you able to formulate the problem into a mathematical forms that may be simplified several assumptions, but still represents the a big chunks of the problem itself, so that the decision that you make is the best decisions considering several assumptions that can be used for as a consideration for the decision makers. However, when you start to introducing several uncertain factors, okay, because this optimization techniques normally assume that everything can be assumes to be have tendency at some point, so we can use a deterministic approach. But when we see in the real case, some situations or most of the problem actually those assumption is not going to be applied perfectly. For example, the inventory case that I mentioned earlier, you will not really know the demand, the precise demand in each day that of a customer that coming to your company or to your restaurant, right? So those are probabilistics, uncertainty, or more detail perhaps like the first, the number of customer is uncertain, what they order will also be uncertain, and the time they come also uncertain, right? Those are from the customer side. Not to mention also when you need to refill your main raw materials to make things, to make products that you're going to sell. The suppliers that you deal with will also induce those uncertainty, right? We are not sure whether the batch coming will always be perfect, right? Something like that. Those are uncertainty that is normally faced in the real case situation. Okay, when you consider those uncertainty factors in your decision making, or you are heavily invested on well, this is this bias affected by the uncertainty is unbearable for our problem. So you need to use a probabilistic modeling techniques or a simulation techniques. And those two techniques are, I think, will be taught in the advanced optimization technique number 2 in our school in the graduate programs. Okay, so I think up until this point, I hope that give you a quite good definition about optimization and OR. Okay, if you have any questions, please keep it. I need to stretching a little bit for 5 minutes, and I will go back and take the rest time 5 minutes. Okay. Okay. See you again, everyone, in 5 minutes.
Okay, sir.
Artvin Ong, do your pose and yoga, and
Well,
share your screen and camera on. I think you're good at.
share to
I
Dr. Wira.
no, I think you're really good at the stretching with
Yeah. I open my
Artvin Ong,
cam since I do stretching.
Artvin, open your camera.
No.
Wear your pants first. So
Yes, Sir Arvin, please turn on your camera.
No.
yeah.
Recording. Okay, so those are three main problem classes in OR, and well, for this one, I think it's good to know, because sometimes you need to sell the things that you are able to do. So wait. So it's good to know when to apply OR and what is its limitations, especially if you deal with some industrial people or managerial level or decision maker in the industry. um, uh, you can sell these techniques by first, of course, knowing what is the benefit of using OR. First, of course, in using this technique, you need to be able to nicely, systematically, logically divine how do you make the decisions. For example, if you want to make a facility location decision, so first you need to mention to them, okay, this is the factor that I'm going to consider for this deciding which facility will be best for your organizations. And after the data, you need to process it this way, and you model it this way. Then those are systematic and logical approach. Okay, and it will be acceptable and make sense for the decision makers. And then the second, by having those systematical thinking and logical thinking, you will be able to facilitate the communications between organization, even though they are from different areas. Because like, for example, if you use the mathematical modeling approach, it would not be in the form mathematical model, it will be difficult to understand by people from various areas. But when you able to make the model speak, I mean, like, make the model able to be understood by communicating it. So this since it's already written or conduct systematically, it will be easier to communicate. There is no hidden hidden factor or hidden assumptions that is being made if you express it in OR techniques or optimization techniques. And well, you can read the rest, but mostly it is reported to have quite remarkable impacts in improving the efficiency and of operations. And you can somehow use the tools, the models that you are developed, to conduct experiments without without affecting the real or the real system on site. So perhaps you can model it. Well, this applied also for simulations. So you can model the problems that you're going to find the solutions, and then you can examine the decisions and see the impacts without affecting the real operations. And okay, those are the benefit, but again, not every problems. Well, OR is not a silver bullet, so it means that some case you may use OR and it works best, but some case you may want to consider other tools, something like that. So it's good to know what is the limitations of OR. First, I would say it's time consuming to, well, sometimes some decisions you just need to do simple analytics, like, okay, compare the pros and cons, then make decisions. But if you make it as a OR decisions, that would be time consuming and takes a long time before you can make decisions. Okay. Decision maker, this one is often, we often find this one in applying OR. Decision maker sometimes reluctant to accept the result of the study because OR is black and white. Like for these problems, the result is this one. This will be the best solution, something like that, right? But in decision making, sometimes there is gray area. Okay, so these kind of things, well, several OR approach are trying to touch those area. That's why I embed some kind the tools, AHP tools in this course. But mostly OR is not common to be used for decision making that involve many subjective opinions from the decision makers, something like that. So you need to be careful about that. But if you treat the technique as recommendations, this will be not offend the decision makers, because the decision will be still up to them, but the result will be the suggestion will be provided by the tools that you are developing using this technique that we are going to learn. And since practical applications will involve many complex considerations, uncertainties, this will be difficult to be modeled or to be solved using OR techniques. So please consider whether your problems after the simplification process still can represent and can be used as a recommendation tools, or the result can still be used to recommend the things without lost many of the generalization of the problems will not lose many complexity and characteristics of those problems being modeled. Okay, it's sometimes called oversimplified the reality. So it makes the recommendation that you make it's unusable for the decision maker. Okay, yeah, those are the most or the point that address the benefit and limitation of OR that you need to consider before using it. Okay, next. Then we will start here. This is just a small part of OR and problems that you may or may not face in the application of OR in real life. For example, assignment problems, whenever you use your ride sharing applications, I don't know what's ride sharing company is big in Philippines. Is it Uber or Grab or
Grab.
other company?
Grab.
Grab or still have Uber there?
No more Uber.
We don't have Uber. Okay. Because in Indonesia there is two competing ride sharing company. We have Grab and Gojek. Okay, and then scheduling, including scheduling many like worker scheduling, including like this one they give quite contemporary example, scheduling TV shows. That's also need OR that can be applying OR techniques. Financial engineering, asset allocation, risk management, portfolio management, and so on. But we will, for this class, we will cover more conventional problems like routing for vehicle routing and then the facility locations. Perhaps network optimization if the times permits. Okay. Uh, I somehow managed to find a video that apply the techniques in airline scheduling, and it's quite interesting. So I may want to stop the recording. So later, if I upload to YouTube, it will not get shoot or something, some problem regarding to the IP. So that's about the video on how OR can be applied to help the airline scheduling to optimize their operations. Okay, it's quite an interesting video. And in that video, they mentioned about linear programming as one of the tools that can be used in OR, and well, basically it's foundations of the optimization tools that we are going to discuss in this course. Linear programming normally used as scientific approach to design to help the decision making by by using the tools of linear programming to make mathematical models. And mathematical model itself is representations of the real problems in the form of mathematical equations and formulations. Okay, well, it's often simplified in a simplified forms due to some problems may be too complex to be addressed or represents in the mathematical forms. So, but most of the models that is discussed of in these books are in the form of mathematical models, and these models is commonly used to make decisions that somehow works like in a prescribed behavior. So it's like we have three level of analytics approach in which we can describe the problems and then we can predict some variables to help make the decision making, or we can prescribe. It means like from the known situation and variables, we will try to make the best decision out of those unknown informations. Those somehow called a prescription approach. So mathematical models and optimization models also sometimes called prescription models. Okay. So in short, that optimization models is commonly used to seek or to find a value that consists of determining decision variables so that it can optimize whether it's minimize or maximize the objective functions among all the set of the value of decision variables being considered. And it's also need to satisfy some given constraints that appear in the problems. So we can say that the main components of these mathematical models commonly consist of decision variables, objective functions, and its constraints. Okay. Other characteristics of optimization problems that address in the linear programmings that also already discussed in the OR courses normally is like whether the model is static or model is dynamics. A static model means that the decision variables being searched do not involve a sequence of decisions. So it's like one shot decision. So you try to represent a problem where the decision variable is the most effective for a particular time frame. Okay, those are static models. Meanwhile, dynamic model is a model in which decision variables may involve in a sequence of decisions because some variables may appear after one decision is made. For example, if you consider assignment problem for a static type of model, so the assignment problems will be fit best for the current time frame. For example, okay, the assignment for the worker in this period, for example, this month will be the best. However, if you consider there might be new job appear during this month, so we need to recalculate the decision. So we need to treat safe sequence of decisions that can handle those dynamic situations. Those can be considered as dynamics models. And then there is a linear and non-linear models. So linear models is whenever the decision variables is appear in the objective function or in the constraints in which there is no multiplications between them or in the objective function or the constraint, so that they will not have the non-linear form of the decision variable. So when you want to suspect whether this model is linear or non-linear, you need to observe their decision variables, the form of their decision variables. And integer and non-integers, this also related with the decision variable. When your decision variables consist of integer number, whether it's binary or integer like 1, 2, 3, like those kind of numbers, then you can consider that model as an integer models. While non-integer, the decision variable may involve real number or fractions, or those type of decision variable will be considered as non-integer model. And the last one is whether you will consider a deterministic or stochastics. Okay, this one we already discussed earlier. Deterministics assume that any value of the decision variables and the parameters for the objective functions are known in advance. So when you are when you're going to use those value, it's assumed that we can use a particular number to represent those numbers. Meanwhile, for stochastics, the value of those parameters or data, or is represent in accommodating the uncertainty factors by representing the data in the form of random probabilistic functions. So those are stochastics models. Okay, now to make it more clear about LP, let's review some LP problems that that already discussed actually in OR class. Okay, first, this is well, okay. First, LP itself, it's a tool, so it's a techniques, can also mention like that, for solving optimization problems. It is first introduced in 1947 by researchers, and I think it's Professor George Danzig, that at the same time develop an efficient method to solve the linear programming, so-called simplex algorithms, in which still one of the best algorithms to solve linear programming problems that is still being taught until recently in the new published books related to OR. Okay, let's see example about this. In general, we can call this an product mix models, in which this model is covered in a story of, for this example, of a wood carving business called Chiapetto's wood carving. Okay, Chiapetto's. I think this name is familiar with people that, I think if you ever listen Pinocchio story, yeah, the store name is Geppetto. Okay. Okay. Now to the problems. The Geppettos, they manufacture, well, it's a simplified case where they manufacture two types of wooden toys, a soldier in the form of soldier and in the form of trains. And it is known that the soldier form can be sold at $27, but it's used $10 of raw materials. Okay. And each soldiers that is manufactured increase the use variable labor cost and overhead cost by 14. Okay, so we have two type of costs. First, for the raw materials. Second, for the variable cost related to labor and overhead costs. Okay, and the same consideration for trains. It sells for $21. Maybe I need to mark it here. Okay, trains sell for $21, and it used $9 of raw materials. Okay. And for train, the overhead cost, labor on overhead cost is $10. Okay, and to manufacture these soldiers and trains, there is two type of skilled labor are needed. The one that do the carpentry, cutting, and then shaping, and then things for making those two products, and the finishings, including painting and stuff. Okay, and a soldier may need 2 hours of labor with finishing skills, and 1 hour of carpentry skills labor. Meanwhile, train is requires 1 hour of finishing and 1 hour of carpentry. And the resources available in this company is that we only have raw material for 100 hours of finishings. Sorry, we only have the resources to do 100 finishing labor and 18 carpentry hours. And if we assume that all the product being made can be sold for the trains, but for soldier, we can only sold 40 units at most. And now, as a researcher that understood optimization techniques, we can apply this linear programming to help this company to gain the maximized profit of the plan to decide how many trains and how many soldiers they need to make the maximum profit out of those plans. Okay, well, of course it needs to consider all those constraints being mentioned, like the finishing labor hours and this one, the most can be sold is only 40. Okay, this is quite easy because it should be the one of the basic things that you can learn and you already learned in OR. For example, okay, first we will decide the denote the variables like x1 and x2. X1 will be associated with the number of soldiers that we are going to produce every week, and x2 will be the number of trains produced every week. And from the, okay, we want to maximize profit, right? So profit can be calculated as revenue minus cost. So you know that the revenue of selling soldiers is $27. So when you see the cost related to make us one soldier is 10 labor hour, 10 materials, $10 of materials and $14 of variable costs related to labor and overhead. So you ends up with 27 minus 10 minus 14 is $3 for each soldier being made. So the objective function will be maximize the profit that is calculated by, for each soldiers being produced, you will get $3. Plus, the same way we can calculate the trains, profit of producing trains, in which we can calculate that train sells on about $21. Then if you minus the raw material cost is minus $9 and minus variable labor cost and overhead cost by total 19, so you ends up with $2. 2 multiplied by x2. Okay. And those are the objective functions being formulated in the mathematical way. And other than that, we also need to consider the constraints that also embedded in the definition of this problem. For example, we know that there is 2 skilled laborers necessary to finish the operations of the manufacturing of these products. We have finishing labor to do the finishing, and then labor to do the carpentry. Each of them has like 100 hours for finishing and 18 hours for carpentry. So it means that from this definition, we know that for each soldier being produced, you will contribute to 2 working hours of finishing activity. And for each trains being produced, it will contribute to 1 working hours of finishing. So the constraint can be written as that 2 multiplied by x1 plus x2 should be less than, because we cannot have more than 100. So less than equal to 100. So this will be the second constraint. And then the same way we can calculate for the carpentry hours. We calculate it as x1 multiplied by plus x2 should be less than 80, because we know there is only 80 hours for carpentry activity. Producing 1 soldier will contribute to 1 hours, and 1 trains will contribute to 1 hour. So 1x1 plus 1x2 less than equal 80. Okay, those are the second constraint. And the last constraint is that since we know we can only sell 40 soldiers, okay, we can only sell 40 soldiers, so don't bother to produce more. So x1 should be less than equal 40, right? Then this is the sign constraint, because the amount of product that you are going to produce should be more than equal to 0. So this is like to make sure that the number is positive here. Okay, and that's the constraints and the formulations of this problem in terms of linear programming approach. Well, I hope there is no confusing things here, because this is just the basic, and it's already being well covered in OR course. Okay, so then how do you solve OLP, right? For the problems that we mentioned earlier, it is quite easy to solve because they only have 2 variables, 2 decision variables, in which we model it as x1 and x2, right? And our job is to find the number of x1 and x2 that maximize the value of z, which is representing the profit being acquired by producing those x1 and x2. And if we draw all the constraint in the nicely depict illustrations like this, because it's only 2-dimensional, we can see that this constraint represent the second one, this one, the third one, and then this one, the last one, because number 1 is the objective itself, this one, right? So here we have the terminology of so-called the feasible region, this one, the one that is marked by gray area. So, well, actually this objective is to find this value of x1 and x2, which are covered in these feasible regions, in which inside this polygon DGFAH, this one. Okay, so from this one, well, actually later on, in OR courses, you may taught how to use the graphical solution approach to get the optimal value. For example, using line like this to find those and it's normally for this type of LP formulations, you may want to check the corner points of each intersection between two lines, or yeah. So for example, D will be get how many, and then G how many, and F how many, and also what E. Well, of course, H will not give you optimal because it's 0 and 0. C equals 0. Okay, something like that. Then another way is to use optimization tools. Well, before optimization tools, actually there is algorithms like simplex algorithms, and then also we can use optimization tools like Excel solver or mathematical programming approach like AMPL and others. Like there is many software that we can use. Okay, but for now, for this introduction class, I will just tell you that the optimal is located where x1 equals 20 and x2 equals 60. It means that it will be 20 and 60 also. It's here, 20 and 60, x1 and x2. Okay. And we also need to know about several terminology when you talk about LP formulations. Okay. In the previous case, we see that there is only one optimal solution. But in practice, we may also find that the optimal solution or the best solutions could be more than one. I mean, like there can be multiple, or we can also call it alternative optimal solutions. That is possible to be happen in the mathematical programmings or formulation of LP, solving problem using LP. And there is also possibility of invisible LP. For example, okay, let's use this graph as the illustration. Let's say if somehow your formulation asking for a region that is a value of x1 and x2 that is located in these two regions and also these two regions. Of course, it's not possible, right? You can also only select either here or here. There is no connection between these two regions. So for this type of LP, this is called an invisible LP, or an LP that has no solutions, no feasible solution. Feasible solution, it means that a solution that agree or follows all the constraint in being defined. Okay, and that's one is invisible. Another thing is unbounded LP. Unbounded, it means that the decision variable are allowed to have a value that is make the calculation of decision variable can be close to infinity. I mean, like the boundary that you make for this particular LP is not necessary give you particular solution. For example, let's say the area is feasible area is here, and then there is no boundary to the right or to the up of the formulation. And in this formulation, you are asked to find the maximum value of x1 and x2. What should you do? what should be the answer? Well, the answer is this formulation is unbounded. The bigger the x1 or the bigger the x2, the value of z equal x1 plus x2 will be close. The best value of that maximize the z equal x1 plus x2 will be close to infinity, right? The more x1 will be raised the value of z. Those are called unbound LP. Okay. Yeah, those are about LP. I think I deserve 5 minutes break after this. Let me break the session for 5 minutes. Okay, see you again in 5 minutes. Next, we will discuss more example of optimization problems. Now, let's involve more variables that might be more have more applications. For example, in production planning and inventory controls. Okay. LP applications in the area of production planning and inventory controls has been studied and how to say, extended by many researchers even until recently. But of course, the formulation that we see in the example here will be the most basic formulations in which it is suitable for the learning process in the class. And okay, take example of this one. I took this example from a book, OR books, that actually it has been revised so many times because it has so many popularity. I think I don't remember which edition is the current volume right now, but this one that written by Winston Wayne and Goldberg is quite a popular one. Besides the one that written by Taha and what else? Lieberman, yeah, that one. Okay, so this one, an example of a multi-period inventory model. So let's say we have a dummy company or just an example of company named Acme Manufacturing Company. It has a contract to deliver 6-month periods of their products called Windows that is being used in home. And the contract said that during this period they need to deliver 100 for the first period, 250, 190, and 140, and 220 and 110. Okay, for the next 6 months. And they need to consider the production costs, including labor, material, utilities for each Windows. And it is estimated that those costs, production costs, for the next 6 months, based on their prediction, is 40, 50, 45, 55, 48, 52, and the last month is 50. Okay. But to take advantage of the fluctuations in manufacturing costs, the company, Acme company, can produce more Windows than needed in a given month and hold extra unit for delivery in the later months. It means that for some case, they can produce more than what is being requested. Okay, and this will incur storage costs. Okay, the storage cost is $8 per Windows per month, and it is assessed at the end of the every month's inventory. So now our task is to help the company to determine how many they will produce every month, and if it is more than the deliver the contract being the contract the product needed or the demand, it will be considered as an excess inventory and then can be used for the fulfill the demand in the following months. Okay, so by using our knowledge of linear programming, we can use the similar step. First, we need to determine the decision variables. We here set the decision variable as x, in which it has index I, xi, where I is element of 1 until 6, in which 1 represents the first month, 2 represents the second month, and until 6 is the sixth month. And
Dr. Wira, can
yes,
you accept Yoshiki? Yoshiki is entering the room.
I see. Sorry. Admit. Okay. Okay, now those are the decision variables. So another decision variables needed in these models is that we also need to consider how many inventory will be left or excess in each month. Okay, because we know that we can produce more than what is requested, and then the rest of it we will use we will consider that as an inventory and can be used to fulfill the demand in the next period or next month. Okay, so this will be represented as I index I. Okay, and the same way I is element 1 until 6. Okay, now we have the decision variables. We need to define the objective functions. Here we want to make a plan of how many units being produced and how many of those units are considered as inventory. So the objective is, from those plan, we want to have the minimum the plan that incurred minimum cost, in which the cost considered here consists of production costs, because how many we produce, and also inventory costs. It means that when we produce more than what we generate, when we produce more than being used, it will become inventory in the next month. So they also have the inventory cost. Okay, for total production cost, it is mentioned in the paragraph or the problem definitions that each month they have different costs. So the way we can this way we can decompose the cost of each month and multiply it by the wake factor. For example, the cost of producing each product every month. So for example, for the first month, it will be multiplied by 50 because the production cost for those months is 50. And so the same way are being applied for the next variables in the next month. For example, X2 is the number of unit produced in the second month will be multiplied by 45. Okay, and so on until the sixth month. Okay, and since we also have inventory, or we may also not have inventory, so whenever we don't have the inventory, the value will be 0. But if we have inventory, we will need to multiply it with the inventory holding cost. Since it's only one period holding, so it's assumed that we cannot hold more than one period inventory. So the model will be the objective function will be written as follows. Okay, then we get the well-defined objective function formulation. Okay, the last is like yeah, this is the constraint that we want to how to say make sure that the production will match the demand. Okay, for each month, and the excess demand will be considered as inventory. Therefore, to match the first month demand, we have 100 demand in the first month, right? So the formulation for the first month demand is total number of inventory produced in the first month minus total number of product produced in the X1 minus the product that you consider as inventory on that particular month. It means what? It means that for X1, the value can be more than 100. Okay, can be 100, and then the I1 will be 0, or can be 120 and the I1 will be 20. So it's a trade-off. You want to produce more, it means you will suffer from a higher production cost, and you will consider that the production cost is lower for that month, so that you consider that, put that one as an inventory and use it for the next following months. Take example, let's say from this case, you know that the first month production cost is 50 and the second month is 45. Perhaps you want to produce more on the second month and then use it as inventory to fulfill the demand on the following months. But before you decide that, you need to consider whether it is beneficial to produce more, since we need to also know how much the excess of production will be affect the inventory holding cost. Okay, those are the trade-off being considered here. But anyway, the in LP formulation, we just need to define it well as a mathematical formulations. Like, okay, this one is the first month, and then the second month, of course, you will have inventory from the last month, I1, plus the production that you have in the current month, X2, minus the number of inventory that you will consider to fulfill demand in the next following months. And it should exactly fill the demands on the second month, in which it is 250. Okay, those things we formulate the same way for month 2, month 3, month 4, 5, except month 6, we will not have we will not consider inventory in 6 months, because there is no 7 months to be filled here. It's out of the consideration in this problem. Okay, So those are the formulation of LP for production planning and inventory control. And okay, it's already 15 minutes. If you need some times to digest the formulations, please take a look again. If you want to raise questions, I will be open for discussion during the break also. Okay, the next discussion is about some more example of optimization problems that also often appears and used in practice or in research. It's called work scheduling problem, in which the formulation is quite similar with the previous one, but somehow this one will have more complex considerations. Well, we will discuss for work scheduling problem in more detail next week. But from this one, what I can show you that, okay, you can see that each mathematical formulation is unique to the problems. Then you might think that how can I formulate one problems that might be suitable with the problems that I'm currently working on. Okay, for those questions, let me try to finish several more examples so that we can help you to we can discuss further on the questions that I just raised, which normally asked by students that new to this type of tools. Okay, this one work scheduling problems. They have more different objective functions, different constraints, and we will cover facility locations in the third week, I guess. The third weeks we will have discuss a lot of models related to facility locations. The formulation will be also, as you can see, it was unique to the problem itself, where you hear the notation is more complex than the previous one, right? And the decision variables also more than the one that considered in the previous examples. But anyway, this basic facility location problems I also already discussed in the last class, because you many of you are from PhD students that already assigned the PhD seminar last time. I think we can see again if you want to revisit the explanation of this model. But anyway, if you not yet never heard about this model, we will discuss. Don't worry, we will discuss this one in the third week of this class. And next, VRP and TSP will be discussed in the fourth or fifth weeks of the this class, this course. So it is also one of the most popular problem being used in the teaching environment, because it also provide, how to say, many application in the industry. And well, I myself also have several research related to VRP and TSP. And the formulations, it's slightly more complex than the previous examples that I mentioned, but still this amount of constraint is still considerably less compared to publications that now I think getting more and more complex consideration in their models. Okay, and this is another things that we will learn in this course is how to use mathematical programming tools to solve those models. And one of the more popular mathematical programming tools is called AMPL. I will upload the software since I already applied for the license related to this software. So I think I can provide you if you need the software to it's a full versions. However, it's how to say they have the full versions uh, being full version program for academics purpose. Okay, so it will not be different with the one that being used in the industry, but academics people are allowed to use it freely. So I think that's good, and you PhD student can also use it for their research purpose. Okay, the problem is only that it has limitation about the time. There is a due date that we need to notice, in which, if I'm not mistaken, I can use it until December 2021. But if you need more than that one, I can actually you can also apply directly, or if not, you can just ask me. I always have the renewables every 6 months. Okay, next, this one I think already discussed this as well in your research PhD seminar. I think I will put the link also. I think Dr. Yogi also uploaded it in his YouTube channel. But basically, what I want to mention here, that optimization technique, if we categorize in analytical approach, it has actually it's considered as prescriptive analytics, as I mentioned earlier, in which prescriptive is more to making the best out of available data or informations, make the best decision out of those information available. And besides the applications in the industry, actually the technique that we learn, like mathematical model, math programming, especially meta heuristics that you will learn after the midterm, can be applied because it's so robust, can be applied even for to help the performance, or to optimize the performance of other methods. For example, you can use meta heuristic to improve your forecasting techniques, to improve your machine learning errors, reduce the classification error, for example, or to decision making in the simulation tools. For example, combine meta heuristic and simulations. Those there are many application of these meta heuristic tools. That's why I insist to add those topics in this class, so that you can use the benefits. Okay, next, yeah, this graph is a simplified one, because well, actually, if you really want to draw the relationship of optimization, this one in terms of the modeling techniques, if you want to make the taxonomy, somehow one model, one category may interrelated.
This is
with
crazy.
yeah, this one I took from
this is what?
it's just the naming, Yogi, just to scare some some researchers.
I mean, what is this?
Like,
I mean, I
okay, so let me guide a little
Yeah.
bit. We are discussing about optimization here. Okay, And when we consider the variables or the parameters being simplified as known in advance, we consider that one as a deterministic optimization, in which we study this one in this course. When we have the decision variables in terms of discrete decision variable, in which it can be an integer or a value that is discrete, we call it discrete integer programming. But if the value of the decision variable is in a real number, so it will consider as continuous optimization problems. Okay, 1, 2, 3. And we will cover integer programming as you see it earlier. And integer programming can be also categorized as combinatorial subset of integer programming, subset of discrete optimization model can be categorized as combinatorial optimization problem, in which the solution is represented as a combinatorial, can be represented as a combinatorial options. For example, a routing problem is combinatorial optimization problems, because when you have 10 cities, actually the sequence of visiting one city until 10 can be represented as a combinatorial one. For example, 1, 2, 3, and then you will not visit 2 again. So 4, 5, so it's a combinatorial type. And for continuous, actually discrete as well, you will have the one that unconstrained. So sometimes it's only objective function, or a constrained one. Okay. And there is nonlinear programming, and this one is already in detail. Several, like the one that we will discuss, network optimization, will be related to problems that consider the problem that can be defined in a graph. So it will be network optimizations, and this detail is like more specialized case. And I'm not sure actually this one is a valid way to do the taxonomy, but I think the guys in that provide this one is quite reliable, since they also provide optimization software in their how to say site. So they actually provide software to do the optimizations online. So we just need to upload our code there and then do the solving, and then they will, after we get the result, they will email us the result, something like that. So okay, this is just one knowledge, but some of this category we will cover in the class, but not all of them. Okay, next. Since I talk about the applications of the optimization technique in supply chain management, so I may want to show you a little bit the history or the how the terminology of supply chain management come in place, so that you can how to say grasp what kind of area we can apply the optimization inside of this supply chain topic. So before 2000, actually supply chain management is not as popular as today. It is sometimes considered as a part of logistics, but now it's the opposite. Logistics sometimes considered as part of supply chain, where logistic itself consists of the category of doing purchasing, material management, and physical distribution. Okay, and these are several activities considered in this area. And when you consider the strategic planning, to do the information and services, marketing and sales, and finance, then it's raised to the terminology of supply chain management. Okay, And okay, this is the definition of supply chain. I think I already also discussed about this in the previous lecturer in the PhD seminar. But basically, yeah, supply chain is a set of approach that integrate all the party involved in delivering your products to the customer efficiently and efficiently and effectively. Okay. This graph also I did cover in the previous lecturer. Means like the decision in supply chain will be associated with the optimization problems that you are going to you want to solve. So when if you think about long-term decisions, so the optimization problems, the objective, the decision variables, the constraint will be also have the characteristic on how to make a decision for a long-term decision. For example, it usually consider the perspective of top-level management, and then the decision will be cover more like a bigger picture of the decision instead of more detail of it. So the final decision will be more subjective. So your model, the model that you develop, the optimization that you develop normally will only be used as consideration or decision support system, decision support tools that being considered by the decision makers. Okay. But since it's so many topics can be covered as optimization problems, we may not be able to discuss all of it. So I just select several one that is popular, and I think it can give a good foundation. But again, if you have other topic that you are interested in and you want to explore and you want to use the tools to those topics, it is also welcome for discuss in this class. Okay, I think those are all the materials for today. Yeah, the rest will be about the assignment. I will post the assignment in the Blackboard, and I think for PhD student, you may already have those.
This is easy for
Yeah,
them.
you already
5
read all those
minutes.
paper, but
Yeah.
I will more encourage you to, how to say, if you want to do this one, it's good. It means like you can, how to say, do this one as a light reading lah, for your maybe more inspirations to be explored on your current topics. Okay.
Kiana, are you okay, Kiana? Undergraduate after here.
Yes,
You still can survive, right, Kiana?
yes. I'm still
Trying.
Are you doing
I
your
know,
final
trying.
project already or not, Kiana?
not yet.
Not yet. Okay, so perhaps this can be also, you can also consider this as your if you want to use as your final projects. I think Dr. Yogi can help for the
No. I cannot do this one.
advisor. Since I think I will not I will be only advisor for PhD student, right? So
If you want, you can.
wait.
You can.
If you want, you can.